Welcome to tutorial number 230 on GHS model creation. This tutorial specifically focuses on part types in GHS. So where have we been so far? So far we've looked at the various tools for model creation in GHS, and we've looked at how a model is organized in GHS. So now we're going to look a little bit more at the individual part types in GHS, what makes each of them special, and more importantly, how you use them in combinations. First, a quick disclaimer. This presentation is for instruction purposes only. It's not to be used in engineering for construction, and I'm not a representative of Creative Systems. Nothing I say has been endorsed or reviewed by Creative Systems. If you are interested in getting the official version of the GHS training, I highly recommend it. You can contact Creative Systems for more detail, and their contact information is listed at the bottom. So the first type of part that we want to talk about in GHS are hull parts. Hull parts, what makes them special is they create displacement. So this is the force that holds your ship up. And they include both an above water and a below water portion in the part. And this is the interesting part because it only adds displacement for the section of the hull that is below the water. Another interesting thing is that hull parts can be negative. They can have a negative displacement. This is especially useful for creating holes in a hull. For example, if your hull had a bow thruster in it, it's actually quite a bit easier to model the shape of the general hull and then add in a second part, which is subtracting out that void of the bow thruster. Some special features that you get out of hull parts. First off, you can model camber. So this is going to be the curvature on the surface of the deck of your hull. That can be significant. You'll also have the margin line. This is useful later on when we talk about modeling damage stability or doing damage stability analysis. And we also have something called effectiveness. Effectiveness is very similar to permeabilities that you would find in tank contents. It's a way of saying that the hull is not a complete displacement, that it might have some form of permeability to it. The next part I want to talk about are tank parts. Tank parts are probably the one element you will model the most in GHS, and that's because ships have a lot of tanks in them usually. There's a lot of fluids that they have to hold. And that's what tank parts do. They hold the weight of fluids. And that's kind of important because number one, tanks, their fluids are adjustable. As a ship, for example, as a ship travels along, it burns fuel, so the level of fluid in its fuel tanks reduces. You can do that in GHS, as you can adjust how much fuel is in the tank. And also, the actual center of gravity of those tanks will actually shift with the vessel's orientation. So if a vessel trims by bow down, the tank contents will shift forward. Their center of gravity shifts forward. That has serious implications for stability. And that also leads to a few special features for tank parts. Number one is permeability. So you can adjust the permeability of the tank part. Second feature is contents of the tank. So this is one of those elements where it doesn't always have to be the same fluid. You can actually say that the fluid is fuel and say what the density of fuel is, or say it's heavy fuel oil and give it that kind of property. And then the other special feature is a sounding tube. Now this can be quite important because the sounding tube is how the operators will manually check the fill level of a tank. It's going to be an actual physical tube in the tank, and sometimes sounding tubes take a very convoluted path to get to the bottom of the tank. Sometimes they're not just a straight tube going down. And the nice part is that GHS can recognize that, and you can model all of those kinks and bends in a sounding tube. Now, there's one last part, and I've saved the best for last. Tank parts include a free surface moment. Free surface moment is probably the most critical thing to a tank parts. And this is the most important thing for calculating stability when considering tanks. So remember how I said the contents can shift with vessel orientation? That all has to do with free surface moment. And there are several ways to calculate free surface moment. Pardon me, I'm getting a little ahead of myself, so I'll go back for a second. There are several ways to calculate free surface moment, and we'll talk about that in a couple slides. But first, I want to talk a little bit more about the contents of a fluid, of a tank. There are two important parts to a content in a tank. First off, that the fluid has a name to describe what kind of a thing it is. This is very convenient for you. And then the second thing is that the fluid has a density. Now, here's one of the key things to remember. Density of fluids in GHS, densities are always set as the specific gravity of the fluid relative to fresh water. Now, that is information that when you're working in Rhino, you can set that information in Rhino, but sometimes you don't have to, because GHS also has built-in tank contents for common types of fluids. So for common things like fuel oil, seawater, you don't have to define the actual type of content. You can just tell its name, and GHS will automatically look up the density. So as an example here, this is the command of how you would actually define the contents of a tank. So the keyword is contents, that's your command. Then we have the description, so that's whatever name you want it to be, a comma, and the specific gravity. So for example, if I wanted to define a new fluid of LNG, it's contents, LNG, comma, and specific gravity. Now, if I was just using fuel oil, for example, I could type just contents FO, because fuel oil, the FO name, is a built-in GHS keyword, and it automatically knows to go look up the density for fuel oil. Okay, let's talk a little bit more about sounding tubes now. So as I said before, a sounding tube it can have multiple segments. It can be just a straight line, or it can lead multiple paths. The way you do this in Rhino is you actually create a line in Rhino. So that's a polyline or a curve, one of those line objects. And then you'll assign that line to a tank. And I'll show you how to do that, or tell you more about that later. But what's really important about that is useful when you're creating tank capacity tables, because those tables are organized by the sounding on that sounding tube, either by a sounding level or an ullage level. And so when you define this sounding tube, GHS recognizes that length along the tube is your sounding level, which is not necessarily vertical position in the tank. Sometimes it might follow the shape of the shell of the hull, for example. Now the command to define this in GHS, if you're going to define it in GHS using commands, the keyword is tube, and then it's a 3-pair coordinate system. So length coordinate, transverse coordinate, vertical coordinate. And you can keep defining those coordinates. So it's just a list of coordinate positions, and here's the important thing to remember. The bottom of the tube is the first coordinate point, and you go from bottom to top as you define more points. You can use a maximum of 255 points, which is quite a lot. I don't think anyone has ever needed that many. So here's just a very simple example. So the command is tube, my first coordinate set right here, so 0, 0, 0, so I'm right at the origin point, and my second coordinate set, 0, 10, 20. So that's saying it's gone 10 meters to starboard and 20 meters above baseline. Okay, and again, saving the best for last. Tank's free surface moment. Free surface moment is quite important, and it actually gives you several options for how to calculate free surface moment. This is something that you set at analysis time. So when you're building your model in GHS and thinking, okay, how do I set the free surface moment for my tank? Don't worry about that. You don't set the free surface moment when you're building the model. It doesn't happen when you're building it. You do it when you're actually using the model in analysis. So we'll come back to that in later lessons. Now, the native capacity, the way that GHS naturally calculates free surface moment by default, is it holds the volume of the tank constant. So if you've said you've got 500 cubic meters of fuel in the tank, it knows it has to keep it at 500 cubic meters. And then it's going to calculate the heel and trim of the vessel and allow the contents to shift. And the free surface, the liquid surface will adjust its orientation, and that changes the center of gravity of the tank. Now, the GHS recognizes that shift in center of gravity. So just keep that in mind for some of your analyses, because some of these can become iterative. You tell the GHS that the ship heels over based upon balancing out its moments. Well, the ship heels over, now all the tanks shift, and so the center of gravity is shifted, and so GHS has to rebalance the ship and heel it some more as well. Now, GHS does that, but just keep it in the back of your head that it's an iterative calculation. Okay, we're done with tank parts. Let's move on to the concept of sail parts. Sail parts are a handy little tool to have. They do not have any displacement, they do not have any weight, they do not contain any fluids. They are just a wind area. So this is just for when you're looking at stability calculations for things like wind heeling moment, and you want to include elements like, well, if you're a sailboat, your sails, or if you want to include things like a superstructure. A superstructure is something that doesn't really have any displacement to it. The structure would never stand up to that kind of pressure, and it doesn't really contain any tank parts either. So you give it a sail part, and the sail parts just catch the wind. They only work in the transverse direction, and here's a real catch, is if you stack sail parts in front of each other, GHS will not automatically assume that there's wind shadowing happening. If you have one part in front of another, it's not going to account for the area deduction. So if you've got, for example, a part with 1 square meter of area and another part in front of it with 2 square meters of area, GHS still thinks your total wind area is 3 square meters. It just adds the two together. Unless you specifically force GHS to calculate wind shadow effects. And we'll show you later how you can do that. A few last things to mention about sail parts. Number one, displacement parts, your hull parts, they also produce a wind area. So if you've got your hull, you don't need to add a second sail part on top of it for its wind area. The hull will already catch the wind area, and it will only catch wind area for the section that's above the water line. And the last thing I want to say is tank parts. Tank parts do not catch wind area. So if you have a tank sitting out on deck and you're worried about the wind heeling moment, you have to create the tank part in that case, and you also have to create a sail part of the same size and shape in that same point, just to catch the wind. Okay, so we've covered quite a bit of information about the various parts, and now what's going to happen is this is really going to be a case of learning by doing. So, pardon me. This is going to be a case of learning by doing. So let's talk about homework number 231. In that homework, you're going to find a drawing of an example hull this barge, in fact. This is the drawing. So if I zoom out, give you a bit of an overview here. And there's the plan view and the profile view. It's a very simple drawing, a very simple barge. This is not intended to be for construction. I'll say that very clearly. This is not for construction. It's just meant to be something for you to work with. So what do I want you to do first? First, create the hull geometry in Rhino. So you're going to create just the hull, and then attach that geometry for a GHS object. So use the command attach GHS data. And once you've done that, you'll create the hull as a single part in that pop-up menu. So you're going to have the whole part, and then you're also going to create the notch as a negative displacement part. So if I can go back to the drawing here, notice we have a notch here in the aft end of the hull. This is an ATB barge, and so this is where the tug would come in. So I don't want you to model it with a section. I want you to model it with this whole part of the hull as one thing, and then add in the notch as a second displacer part that has a negative displacement. And once that's all done, you can actually do a file save as in Rhino and save it as a GHS file, open it in GHS, and check your work. Once that's done, we're going to roll on to homework number 232. Now, if you had any problems with homework 231, the solution is also provided in there. And we're going to use that as the basis to now work with homework 232. So I want you to take that hull geometry that you've made and add in all of the tank parts. Now, a couple catches. First off, the engine room has 2 tanks in it. So if we look right here, this is our engine room, and this is common enough at times. Many barges have auxiliary engines for some form of power. And notice the engine room has 2 tanks inside of it, a lube oil tank and a hydraulic oil tank. So the way I want you to model those is first create the entire engine room, and then deduct those 2 tanks from the engine room. So you're going to create those 2 little tanks as their own little things, and then you're going to deduct them from the engine room. You'll use that as a negative volume. If you can, also try to define symmetrical tank parts from the same shape. This is all being done in Rhino. You can still use Rhino for all of this. And finally, leave the contents and all the permeability for your tanks set at their defaults. We're not going to worry about that yet. And of course, there's a solution provided for this. Once you've got all of that defined in Rhino, you can save as a GHS file and open it in GHS to check your work. Once that's done, move on to homework number 233. Now, I know it's a lot of homework, but it's really the best way you're going to learn about the different hull parts, tank parts, and sail parts, and all the things they can do. So now we're going to go in and customize those tanks. I would like you to assign the specific permeability to each tank and the specific contents to each tank. And there's even 2 custom contents that you're going to use. One is LNG, which is liquid natural gas, and another one is the engine room that has a tank content of air. Now, where can you find all this information? If you go back to this plan of the barge, go to sheet number 2. So sheet number 2 lists all the information that you will need for each one of these tanks. So notice for every tank, we've specified the permeability of the tank and the contents of the tank, what their names are, and the specific gravity of those contents. So all of that information is there for you to work with. And you'll notice that all of the tank names have already been set up as GHS part names. And then finally, once you've gone through and assigned all of those tank permeabilities and tank contents, if you're still up for it, define sounding tubes for each tank. So again, the way you do that is first you create the lines in Rhino. They're just straight lines. Then you go back into your attach GHS command, and for each tank, you're going to press that set tube button. Set tube. And then that will allow you to select the line that you want. You just click on the line and it's now assigned as the sounding tube for that tank. And of course the solution is provided as well for homework 233. Finally, homework 234. We're going to build on the last homework again, and what you're going to do this time is add in the sail area of the containers. So if I go back to our drawing, notice here in profile there are all these containers on the top of the barge, and they're actually stacked in rows. You've got 1, 2, 3, 4, 5, 6 rows of containers. These are standard ISO containers. So what I would like you to do is create one sail part for each row of containers and have them stretch across the full width of the deck plus the full length of the hull based on the dimensions you see in that drawing. The reason you're doing one row or one part for each row of containers is later on when you get to stability analysis, it's useful to be able to turn off one row or another if you're not sure how many containers the stability of the ship can take. And then you're also going to add in the skegs to the bottom as a non-displacement part. These are free flooding skegs. Now, how do you do that? Well, again, you're going to first create the geometry of the skegs in Rhino, and then you're going to attach them as a hull part. But here's the key part. Once you've attached it, change the properties, set the effectiveness of the skeg to 0. Effectiveness is the key word. And for all of this modeling, use the actual dimensions from that drawing. Okay, well, thank you very much. I hope you found this video informative and useful. You can find all of the homeworks and more videos like this on dmsonline.us. Thanks very much. Thanks for watching. I hope you liked it. Hey, did you know that there is a magic button down below? Click the like button or even the subscribe button and I will make more videos for you.